in this module we are going to graduate from looking at just vacuum. We are going to make the first steps to look at situations where there are realistic materials, okay, and also boundary conditions. How will we impose boundary conditions, right? So, we are building the FDTD up in complexity step by step. So far in vacuum we looked at the main things. How do you set up the computational cell, how do you look at stability, how do you look at convergence and accuracy, all of those things, right. Now, let us look at materials. Okay. So, we will start with dielectric materials. Okay. Now, your Maxwell's equations said, for example, curl of H, right, and supposing I have a dielectric material. So, what is the constitutive relation I used? How would I introduce the permittivity of the object in here? Epsilon needs to come in, right. So, what I would do is put D is equal to epsilon E. Okay. Now, one of the main things that I want to sort of challenge in this section is our use of this equation. So, what we will find out today is that our use of this equation is actually been very flawed throughout. So, we will try to put this on a proper footing now. Okay. So, for now let us just assume that this equation is correct. So, then what would happen is that you would simply have this equation would become epsilon E dot is equal to curl of H, correct, and that is how we deal with in any E cell. I assign the permittivity to be epsilon 1, epsilon 2, whatever, right. So, this is then fixed appropriately okay. Yes, okay. So, what supposing this is your computational domain, right. So, what our E cell is going to fracture this whole thing into a square grid. That is how we do it. And now, this over here, this has some epsilon 1. Okay. So, first of all, what I do is I do a piecewise constant approximation of epsilon. So, wherever there is a square grid, I assume the epsilon is constant over there. So, this is some epsilon 1, this is some epsilon 2 and so on, right. So, on this grid, once I fix the values of epsilon, then I use these update equations with the appropriate value of epsilon or mu, right. I will also replace B is equal to mu H and put those values of mu, right. So, epsilon and mu's per E cell, okay, and usual update equations. Okay. Now, what if my material also has non-zero conductivity? How will my update equations change then? Yeah, there is a lossy thing. So, how do I deal with it? Complex permittivity is one thing, but when I do complex permittivity, the implicit assumption there is that I am going to I expand the fields as in the e to the j omega t form. If I do not want to do that, I want to stay in the time domain, then how do I deal with introduce a new component? Yeah, how do I introduce it? So, let me just write this. So, deal with conductivity. First of all, so there is a j term. First of all, this Maxwell's equation, is it complete or there is something missing in it? The j term is missing, right. So, what actually is there is that curl of H is equal to dd by dt plus j, and j I can replace by, and that is what law? Ohm's law, right. So, Ohm's law right. So, then this equation this update equation becomes curl of H is equal to, so let us say epsilon dd by de, sorry not d, de by dt plus sigma E. Now, let us put this into our FDTD notation. Okay. Supposing, so I am going to remove the vector sign, okay, it's understood from now, by now. So, curl of H, supposing I am updating the electric field at every integer instance, that is what we are doing. So, then the magnetic field is updated at half integer, right. So, for example, I will write n minus half over here and epsilon E dot at n, right, n minus half the same time instant, okay, plus sigma E n minus half. I have just written down the whole, the whole equation in discrete form. If the left hand side is at time n minus half, the right hand side should also be at time n minus half. Now, this is not a problem because I am implementing this by finite differences. So, what does this actually amount to? E n minus E n minus 1 by delta t, right, finite difference in time, and the approximation is most accurate at n minus half. So, it is consistent, right. You agree with me so far? So, what is the problem now over here? I was storing electric field only at integer time instance, but now this equation is requiring that I also needed at half a time instant. So, what should I do? Average it, right. I do not want to be storing electric field at half time integer instance also. So, the best thing to do is to replace this term by E n plus E n minus 1 by 2, right. So, this is average and this is finite difference, okay, and this is as before, okay. So, this is how you would deal with a material that has conductivity, right. Now, in your leapfrog system, what all do you need? So, supposing say you want to update E n, what all do you need to know from this equation? I need to know, let us start from the farthest back in time. I need to know E n minus 1 and I need H n minus half, okay. So, I can do the my update equations are slightly modified from before just because I have a sigma term has come in over here, okay. So, that is just some small thing to keep in mind. So, this is your simplistic way of dealing with dielectric materials, okay. Questions? Okay. Now, what we could do, we can simplify this expression that I have, this update equation. I can simplify this. Typically, I want to update for E n, so I will bring E n to one side and everything else to the other side, right. So, I can do that simplification. So, for example, what will I get? So, try to work it out. So, E n, I have a E n minus 1 and a H n minus half, right. Those are the two terms over here. So, the first term that I get is, I will just write the final answer, which simple manipulation gives it to you. You can confirm that that is also what you get. Okay. So, this is our update equation, and just plug in the values of sigma and epsilon. So, remember here in what we have done, your epsilon here is referring only to the real part, okay, and sigma is the conductivity, that is giving the loss part.